Another important block in the microcontroller that we will almost always use is the ADC block. So let us learn how to initialize the ADC also. Let me make space there. After the initialization of the timer set of statements, I will say initialize ADC for free running mode. So what we do is that we will initialize ADC for free running mode, which means that it will keep on taking the analog value and converting into the digital value and placing it into the ADC register. Continuously it will be doing that. So whenever the timer is set giving an interrupt, when it gives the overflow interrupt every cycle, it will take you to the timer 0 overflow ISR, and in the ISR you can read the ADC register value, whatever the value is there, will put into the result, and then you can operate on the result. That is the way the ADC will also come into the ISR routine. So let us initialize the ADC, and as before, you have to look into the data sheet, keep your data sheets ready, handy, and let us go to the ADC section. Read the ADC section carefully. There are a couple of registers that you need to carefully understand, and these registers you will have to give a control word, set it so that it will control the operation of the ADC. One is the AD mux. The AD mux is the ADC multiplexer selection register. The ADC, there is one single ADC in the ATtiny 85 with 4 channels, which means that there is a multiplexer which will multiplex the 4 channels and will be passed on to the ADC for conversion. So this is the AD mux register. It has 8 bits. Mux 0, mux 1, mux 2, mux 3. These are 4 bits which will define which channel to choose. And there are 2 bits here, ref S1, ref S0 and ref S2. These 3 together decide where to take the reference for the ADC. And then there is a add LAR, which means after the conversion, whether to shift the data left or right. If this is 1, the result will be shifted left and then the value taken out, or it will be right shifted and taken out. So if you go to ref S0, 1, S2, 0, 0 would mean VCC used as the voltage reference voltage reference. So what we will do, one way is to use 0, 1 for ref S0 as 1, which means that VCC will be used as the reference. So this can be 1, this will be 0, this will be 0. Add LAR can be 0. And the mux, if I choose channel 3, it will be 0, 0, 1, 1. So therefore, I can have something like this: 0, 1, 0, 0, 0, 0, 1, 1. This can be the control word for the add mux. Let me go back to the program and appropriately include the control word. So ADMUX. So that is having ref S1, ref S0, then as you see, ADLAR, ref S2, ADLAR, ref S2, mux 3 mux bit 2 mux bit 1 mux bit 0. So we had said that ADMUX can be equal to 0B 0 1 0 0 0 0 1 1 if you want to choose the channel 3. But the better way, recommended way, is to use the bit variables. So if I use the bit variables, then I need to do it in this fashion. So let us say ADMUX. ADMUX, I will let me set the channel. So 1 mux 1 I'll set, and I'm going to also set ORing it with mux 0. So this is done. I also need to set ref 0, so I will OR that also. Ref S0. So that this will set all the bits that I need for ADMUX. Then after that, for free running mode, ADCSRB, there is a ADCSRB and ADCSRA register. Set this to 0 for free running mode. For free running mode, no change. So default set to 0. And then enable ADC start conversions. ADC SRA. This will enable the ADC start conversions. So for ADC SRA, so ADEN I will set, ADSC I will set. ADEN is enable ADC. ADSC is also set, means start of conversion started. Then auto ADC, ADATE set means that auto trigger enable has been done. And all this being 1 means that 111 implies that ADC prescaler is set at 128. So this can be adjusted depending upon what should be the speed of conversion that you are expecting and the frequency of your sampling times. These 3 values. Again, look into the data sheets. So if I go back and look into the data sheets, you will see down here ADCSRA. So these are the bit positions that you should see, and look at the description here so that you can set it appropriately. So this will initialize the ADC for free running mode of operation. So it is converting and then it is capturing. Now here you have to go and write some code to read the ADC. So in the ISR for timer overflow, let me add a bit of code for reading from the ADC. So let me comment read ADC. So first step is to wait for the ADC conversion to get over. The ADC is in free running mode and it is converting the data. Wait for it to complete conversion. Means while ADCSRA, look into the data sheet 1 ADSC. What it basically means is that we are waiting for ADC conversion to complete. You see, while the conversion is an operation, ADC bit is set. ADSC bit is set during conversion. So once that becomes unset, then it will come out of the while, and then we are ready to transfer the data from the ADC register. So let me now read the value. So unsigned int 8. So let me declare this low variable and read from ADC low register. So read the low byte first, then uint 8 high byte high ADCH. Read the high byte. So now shift transfer it to a variable, a 16-bit variable. I'll call that ADC value. So the high byte, shift left 8 times, so it becomes the MS bit. To that you are the low byte. So this will be the 16-bit word that is put into ADC value. So ADC is actually a 10-bit output. So you need to put it into a 16-bit word. So let me give this command: combine low and high bytes to get the value of the ADC. So this will read the value of ADC. So this is in the ISR, timer overflow, timer 0 overflow ISR. So when you start the program, the initializations are done first. They are placed in the main. The timer initialization, then followed by the ADC initialization. Then it goes into the while loop and then keeps circulating in this while loop till an interrupt occurs. So which is the interrupt? It is the timer 0 interrupt we are waiting for. Whenever it hits the bottom every PWM cycle, then at that point the program counter will jump to the ISR timer overflow interrupt vector as per the interrupt vector table addresses. So it will jump here and first read the ADC and wait for the conversion to complete, then read the low byte, high byte, and then we club them together. So this is the ADC output value. We can process it, and based on this ADC value, one can make the duty cycle dependent on that. Here I have kept duty cycle constant when we are doing for the PWM. It can actually depend on the ADC value, and based on this duty variable, the OCR0B will get defined, which will the compare register for the PWM timer 0 compare register, and it will appropriately modify the duty cycle at the PWM output, which will be coming from the PB0. So right now the code is becoming so longer and longer, and once the application starts becoming bigger, it may become unreadable, and as time progresses you may forget what it is. So you need to make it a bit more modular. Not only that you need to use it only for this particular application, If it is modular, you can then use the same code for many different applications having the same structure. So what do we have to do? We have to break up the various pieces of codes into functions and keep them in separate files and call them accordingly. Let's see how we go about doing this simplification. So let me start by including in the source directory here, right click, add new file. I will say my pwm.cpp. That is one file that I add. Also will add one more file for ADC, my adc.cpp. So the idea is that all the functions related to ADC, I will put them in one file. All the functions related to PWM, I put them in one file. So the main will become just light and contain only the template of the application. So let me go to ADC, and here you can give some comments, line comment. So I'll just say this file is my adc.cpp, and this is created on, let's say, 25th April 2025, and let's say author. So like this, you can include some comments there at the top. Then let me add void. So let's say ADC init. We'll call it ADC init. We need to pass which channel you want to initialize and capture the data. So let's say you int 8 channel. Channel number can be 0, 1 to 4. So we give a value from 0, 0, 0, 0, 0 to 1, 1. And then we open the braces and write the code in between. So what code? The initialization code. We have already written this code. Let us go to main.cpp and go to the initialization part. So this is the initialization part. I will leave this comment line, and I will copy all this. I'll copy that, go to ADC and paste it here. So that's pasted here. Okay, so you see that it is not recognizing these identifiers. So I can have this include avr/io.h and include avr/interrupt.h. So let us have that. So now that it is recognizing. So this is one function for initializing. So in the CPP, I just have to call initialize. So I have to give ADC init and channel number. So let me go here. So all this will get deleted, and I will say ADC init and channel number, let's say first channel 0. So this I will comment saying that initialize ADC channel 0 or ADC 01. So when in doubt, always check the data sheet. Here is the pin configuration. Here it is ADC 0, ADC 2, ADC 3, and this is ADC 1. So 0, 1, 2, 3. So ADC 0 is PB5. So you give the analog signal to PB5 for conversion. So you can say that the first channel ADC 0. So let me go back here. So this is ADC 0 is PB5 in free running mode. So that's it. This is one statement. Look clean. And then next, we can also have ADC read. This is reading, ADC read. I can put that as another function in my ADC. It's a control copy. Go into my ADC. I'll have one more function. U and 16 ADC read So the ADC read function, it will return a 16-bit value. I'm not passing any input parameters to that because it is a free running mode. And within this, I will cut and paste what we had in the ISR. So here, ADC read in the ISR, we had this. I will copy that, go to ADC CPP and paste it here. So I will give these spaces here. Yes. So now that this is a function, I will substitute this with a return statement. So return high part or with the low part in this fashion. And I will remove this. Yes. So this would be the ADC read. And where this should be called, this should be called in the main.cpp where we had this ISR part which was reading the ADC. So I will replace this with ADC read. So I'll delete that. Uint 16 ADC value equals ADC read. So this will read the value of the ADC. I'll put in a comment, read the latest converted value from ADC. So you see, this is ADC read. Likewise, I should do for the PWM also. Let me save everything. Save all. I will save. So you see here that main.cpp, it is showing 2 errors already. That is basically it is not recognizing ADC read function because we have not yet declared it. We will declare that. And ADC init is also not, it's not able to, it says undefined. So we have to declare that. We will declare that. Few more functions let us include. Initialization of the timer, PWM timer, and then we will declare all the functions together. In a similar way, let us prepare functions for the PWM. So I'll go to the PWM, mypwm.cpp, and create comment. So let me enter these comments. So file name, let's say my pwm.cpp, then created on, let's say 25th April 2025. Then let me also give author. So then next I will also include avr io.h, then include avr interrupt.h, void pwm init. No parameters are passed, open parenthesis, and here we write the code. So we have already written the PWM initialization code, timer 0 initialization. Let us bring that out here. Go to the main. So this is the timer 0 initialization up to the point where we are defining the PWM output pin. Copy that and go to PWM and paste. So this is the initialization of the timer 0 part with all the comments. And in main.cpp, I will delete all that. I will delete all this and say pwm init. Initialize the timer counter 0 for fast PWM operation. So give the comment like that. So let us now that this part has been compacted in the main program, in the ISR program, let us put this also into a function. I'll call this one as PWM or fast PWM. So let me copy that. Go to my PWM. So in my PWM, I will void PWM fast. So I need to pass a parameter. We have this duty uint 8 duty cycle and open braces. So here I'm going to paste this. So uint 8 duty is 100, so that is now passed as a parameter. So I don't need this line. I don't need that line. And OCRB is a function of this duty. So now this is done. I can go back again to main.cpp and I will replace this part with PWM fast duty. So comment is I'm calling the fast PWM operation. By setting, or let me say, set the OCR0B for dynamic PWM duty cycle change. So now you see that everything is compacted in the form of functions and they are placed in the modular mypwm.cpp and myadc.cpp. If I'm having control, next I will, when I discuss the PI controller, you could have one more module, mycontrol.cpp, and have control value and have a control algorithm in between ADC and PWM. Then the ADC value can be passed through the controller and the output of the controller will give the duty cycle, which can be used to modulate the pulses. So for now, I'm keeping a fixed value of duty cycle here, but later on, after we discuss how to design PI controllers, we can include at this point here this line 17, the PI control function. So now what remains is that ADC read, PWM fast, PWM init, it's not int, it is PWM init, and ADC init, they all need to be recognized. So we need to define them. So here I will place a H file, my functions H file, which within which I can define all the prototypes of the functions. Let us do that. Let me go to this include tab, include folder. So I will include a new file. I will call it my functions.h. So that is my functions.h. Again, I will have the comments line. I'll say this is my functions.h, created on 25th April 2025, author. So we have the header. So this is what I will do. If not defined, my functions H define my functions H this way, define that, and let us have this. So what are the functions? So we had the following functions. We can go to the main.cpp or we can go to ADC, these two functions. Let me copy that. This is one for the ADC init. Let me copy that. Copy. I will click on my functions, place that there. Then again to ADC, this is another function, and I'll go and place it here. Then we go to pwm.cpp. There is pwm init function. Let me go and place that here. Then in pwm there is one more, void pwm fast. Control copy and place it in functions. So these are the 4 functions that we have done, and I'm placing it there. Then close that. End if of my functions. So this is done. Save that. Let us come to main.cpp. So here I need to include #include my functions.h, include that. And you see that ADC read is now recognized, PWM fast is recognized, PWM init is recognized, ADC init is also recognized. So this way you would have kind of made a modular template for the applications. So you will see that this will keep growing depending upon once PI controller comes, you will have a PI controller function coming in, and the modular setup is such that whichever be the application, this will look similar. Almost most applications. Only what will change is these set of modular functions. So you can see that this generic code main.cpp with all the function modules and the myfunctions.h that has been incorporated, there appears to be no error indicated here. You can go down to platform IO build, this tick icon, build it, and you will see that it has built the firmware.elf and the hex with the success, and the hex file will be ready to be ported onto the microcontroller. So this is the template that I wish all of you will use for any of the applications, with minor modifications in the initializations and modifications in the ISR routines.